Here are the answers to the synthesis questions on the practice worksheet. We take this secondary alcohol and we turn it into this ester. So the first thing we want to examine is that it appears that the whole portion of the molecule from the alcohol to the left is the same as from the carbonyl to the left in the product. So all we need to do is somehow turn this into a carboxylic acid derivative and get it to be the ester version of that. And so to do that, we've got a methyl group. We need to lose this carbon, or we need to insert an oxygen between the methyl and the carbonyl. If I have a carbonyl here, could I do a Baeyer-Villiger, where we use metachloroperoxybenzoic acid, to insert an oxygen here? I believe that the tertiary side will migrate first versus the methyl side. So I think we'd get our oxygen right here. We'd make the ester in the wrong spot. So I don't think we can use the Baeyer-Villiger here. However, there is another way to basically turn this group into a carboxylic acid, and that is via the haliform reaction. So first reaction is PCC to make the ketone, then the haliform reaction, excess NaOH, excess Br2, that's a very poor R, and follow that up with acid. And there's my carboxylic acid. Now I can easily go from the carboxylic acid to the ester. There's a couple ways to do that. The first one might be to deprotonate carefully, add methyl. Another way might be to just mix methanol and catalytic H2SO4. Do the Fischer esterification. Either one of those would work fine. Let's look at the second question, or the second synthesis problem. We're taking bromobenzene and we're reacting that to form this much more complicated looking molecule. Okay, so the first thing that looks at me is that the alpha-beta unsaturated portion of this molecule seems to tell me that we're taking maybe an aldehyde that looks like this top portion and condensing it with the same aldehyde in an aldol reaction. So if we look at that, NaOH heat, and you can see that this is the aldehyde that we would want to use. And if you look at the bottom part that I'll circle in green, that's actually the same aldehyde, except it's acted as the electrophile in this case. So I can just take this aldehyde and basically self-condense it to make this alpha-beta unsaturated aldehyde. So this is an aldol condensation. So how do I get to this aldehyde then? I'm starting with bromobenzene. I want to add, looks like 2 carbons and end up with an aldehyde on the end carbon. Well, I can add 2 carbons with a functional group on one of them via an epoxide. And I can add an epoxide if I have a Grignard. And when I add the epoxide, I get a primary alcohol. I can oxidize to that primary alcohol with PCC. That produces an aldehyde on this carbon, and I get my desired aldehyde here. Aldol condensation can bring me to the product. All right, so this one 1-pentene, reacts to form this molecule with a phenyl ring and an extra methyl group. So the extra carbons are the methyl and the phenyl here in the product, and they're both going to be attached to this carbon on the far right of my starting material. So I need to make 2 new CC bonds, How can I do that? Well, I can probably do that via a Grignard reaction. And if it certainly looks like there's no functional groups present here, I could probably remove the functional groups by reducing a carbonyl or reducing an alkene all the way to an alkane. So if I end up with any functional groups after these additions, I can get rid of them with reduction. So let's turn this into something that might be able to add carbons. And that would be an aldehyde on that end carbon there, because that can receive Grignard nucleophiles. So we'll start off by putting an OH there. We'll oxidize that. Now I have an aldehyde, and I could add a carbon group to this. Let's just add methyl using a Grignard. And if I want to add phenyl to this, I need to reoxidize it and add a phenyl Grignard to this molecule. And work it up with acid. I get this tertiary alcohol. How do I get rid of this? Well, if I eliminate the alcohol with E1 type conditions, I'll probably form that alkene, and I can of course reduce the alkene with H2 and palladium. So I've removed the functional group altogether. Let's look at the next option. Again, I'm going to use 1-pentene. This looks like a totally different outcome in this case, though. I've got an ester, and then I've got a phenyl ring on the alpha carbon of the ester. So I'm going to make the new bond right here, and this carbon needs to get a new functional group. But you'll notice that both functional groups or both bonds or whatever I have to add to this are still added to where the alkene used to be. And so I'm making a new bond and then ending up with a new functional group. That's a pretty good indication that I might have used an epoxide to open the ring. So let's think about that. What if I made an epoxide? And what if I reacted that with phenyl Grignard? Which side would be more likely to open on this epoxide? I think it's going to be the less substituted side. That would give us this setup. Is that going to help us get to the product? I don't think so. So I don't think an epoxide is the right way to go. It was a good thought, and it was good to explore that, but I don't think that's the right direction. So what if we thought about it as, well, I can make that ester from a carboxylic acid. I can make the carboxylic acid from an alcohol in that position. All right, so the first step would be PCC, or I'm sorry, Jones reagent. Second step would be ethanol, acid catalyst. So oxidize to the carboxylic acid, then perform a Fischer esterification. How can I now get to this alcohol from my starting material alkene? Really, the only way to add the phenyl group is to maybe put a carbonyl at the second carbon. So I can do that with H2SO4 and water, giving me the alcohol. I can oxidize that with PCC, Swern, Jones, whatever I want in this case. And I can install the phenyl ring now with phenyl Grignard. It might be useful here, just not when we had the epoxide and acid workup like that. So now, how can I get from this tertiary alcohol to the primary alcohol? I could tosylate this, turn it into a good leaving group, and then I could hit it with a strong, bulky base that would remove this hydrogen here preferentially, giving me that alkene and BH3 THF can put an OH on the outside portion of that alkene. So there's my stepwise process. First thing to do is to create a good electrophilic position at the second carbon of my alkene, then hit it with a nucleophile to put the phenyl ring on there, make the carbon to phenyl bond. Then I want to make my OH into a good leaving group. I can eliminate that leaving group in the less substituted fashion using a large bulky base to get here, and then I can install the OH on the outside and oxidize that all the way to the ester. Next problem. Taking this bromine. Looks like we're increasing the functionality quite a bit here. We are ending up with a methyl ether and an ester on the two carbons here. So these are the carbons that we're going to focus on. We aren't really making any new carbon-carbon bonds in this case. We're just ending up with two functional groups on those two carbons. And that's a big clue right there. If we're making two functional groups on adjacent carbons, that's a good indication that maybe we had an epoxide somewhere in the mechanism. So we know that we could end up with this. We just saw this on the previous question. If I have this primary alcohol, I can certainly oxidize it. And then I can react it with ethanol and catalytic acid to turn it into the ester. So if I get that primary alcohol, how can I make that primary alcohol? I might be able to ring open an epoxide with some sort of methoxy or methanol if I can make it ring open on the tertiary side. So what if I had an epoxide here that looks like this? Could I ring open at this position with a methoxy or maybe methanol? I think under acid catalyzed conditions we can ring open at the tertiary site, leaving us with the primary alcohol on the end and the new methyl ether right here. So I think that's a good strategy. Of course, I can make this epoxide from the alkene, and I can make the alkene, I think, from my starting material. I'm going to use a large base here because I don't want to risk the base acting as a nucleophile because this is a primary alkyl halide. So I'm going to use a large base to eliminate, and then I can make the epoxide. I think I need MCPBA here. Once we have the epoxide, we can ring open at the tertiary side with alcohol and catalytic acid, giving us the ether on one side, alcohol on the other. Oxidize that to the carboxylic acid using Jones reagent. Then we can do a Fischer esterification as our final step. Here we're taking benzene. I don't want to use red. And we're taking it to a substituted benzene ring. All right, so there's a couple ways we can look at this. We've got, let's see, one way might be to say, well, I've got an alcohol that I could eliminate, right? H2SO4 will eliminate the alcohol. Although, I'd say it's hard to prevent an equal amount of that alkene from forming. So I don't like this route now that I think about it a little bit. I don't think that's going to work. So that's going to give us basically 50% of the product. We want to try to maximize our product yield. What's another way to make that alkene as the final step in that position? Right, so an elimination might not work. There's another way we could do that. Let's erase this here. Another way we might be able to work on this. What if we had our alcohol right there? how would we make that? I'm not really sure. Maybe we could make that bond via a Grignard and an aldehyde. I guess it's possible to put a Grignard at this position right here, but I think that's going to take a lot of work. There's another way to make this alkene that I think is probably the best way, and that's starting with the ketone in that position. And we can use a Wittig reagent. Remember that a Wittig reagent has a negative charge on the carbon, positive charge on the phosphorus, and it basically replaces the oxygen of the carbonyl with the carbon group and retains the double bond. We can get to this product, or intermediate, from methylbenzene and the appropriate acid chloride and aluminum trichloride. And I'm pretty sure you all know how to get to methylbenzene from methyl chloride and aluminum trichloride. So I think this is the best way to go. Trying to eliminate an alcohol is going to be a little tricky given the region, or the regiochemistry of this alkene. It's equally likely to perhaps create an alkene here that is not the desired product. Second to last one, we take this alkene with a T-butyl group attached to it, and it looks like really all we're doing is turning it into an acid chloride. Let's count carbons just to make sure that we know where all the carbons are. And you can do this in your head too, of course, but I think it's good practice to write it out. All right, so it looks like we lost carbon number 6 somehow, and we ended up with an acid chloride. So an acid chloride, of course, can come from a carboxylic acid. I think that's the most likely place to get it. How can we create a carboxylic acid on carbon number 5 and lose carbon number 6? Well, there's a couple of ways we could do this. I'm pretty sure this is the last step, though. SOCl2 plus the carboxylic acid. So have we learned any reactions that might just cut the bond between 5 and 6 right off the bat? And I think we have. It was first semester. It's ozone followed by DMS workup. And that's going to leave us with an aldehyde. Do you know how to take an aldehyde to a carboxylic acid? Well, we could certainly reduce the aldehyde to a primary alcohol. We could oxidize with Jones reagent, and that would be that. But really, Jones reagent will also oxidize the aldehyde, because the aldehyde is an intermediate. The aldehyde is an intermediate in the primary alcohol being oxidized all the way to the carboxylic acid. The first step is to make the aldehyde. The second step is to oxidize that aldehyde further. So there's really no reason to reduce the aldehyde in this case, just oxidize it. So we cut off carbon 6 with ozone and DMS, and we made the aldehyde, oxidized that to the carboxylic acid, and made the acid chloride. Some of you might be wondering, why couldn't I somehow get to this ketone and then do the haloform? Well, there's a good reason for that. Can you think of that? Why is this haloform not a good option in this case? The reason is we've got certainly 3 alpha hydrogens here that we could replace with bromine, but we also have 2 more right here, and chances are some or all of those would be replaced with bromine, and we'd get a couple bromines at this position as well. And obviously in our product that is not desired. So that's why I chose not to use the haloform reaction in this case. One final synthesis problem for the Exam 3 practice worksheet. This is taking benzene and derivatizing it. That bromine, I think, is in the bottom, so I'll just move that over. Okay, so we have an ortho-para director on the ring here, and we have another ortho-para director on the ring. So neither of these can be used to put the other group on the ring. But what we have also is we need somehow a meta director on the ring that can allow us to install these two groups. This is an ester, and we know that esters can be created from carboxylic acid derivatives. Maybe you think, well, what if I had a phenol here? Still, both are ortho-para directors. Now I'll give you a hint of the amine chapter. At some point in the last chapter in our semester, we're going to learn how to take a nitro group and eventually turn it into an OH group. And so that might work in this case, but we haven't learned that yet. Certainly not, well, that won't be on exam 3, so this isn't going to work. So let's not go with that. We have learned another way to install esters, and that's via the Baeyer-Villiger reaction. So what if we install that O between the ring and the ester? And this molecule should look very familiar because we've made many of these versions back in chapter 19. So this is now a meta director. We could use it to install the bromine, FeBr3. And we can certainly install that with Friedel-Crafts acylation. And let's see, making the, so getting the phenyl to migrate versus the primary carbon, the phenyl is more likely to migrate. And so all we have to do is write MCPBA, and that's going to do the Baeyer-Villiger reaction. So you can see that the Baeyer-Villiger can be hidden many different ways. It allows us to take a ketone or an aldehyde and turn it into a carboxylic acid derivative. So you might see this again in the future. But anytime you see an ester now, you can think, well, could that have come from a Baeyer-Villiger? Examine the two groups that would migrate, and in this case, the phenyl has more migratory aptitude than the primary carbon here. And so indeed, this ester could have come from a Baeyer-Villiger oxidation.